On a dark, moonless night, far from city lights, look up toward the constellation Andromeda. There, barely visible to your naked eye, is a faint smudge of light, a ghostly patch that doesn't quite look like a star. That delicate glow is the Andromeda Galaxy, and what you're seeing is absolutely mind-blowing. Today, we're diving deep into one of the universe's most magnificent structures, our nearest major galactic neighbor, a cosmic giant that's racing toward us at over 100 kilometers per second. If you're fascinated by the breathtaking scale of cosmic structures and want to explore more wonders of our universe, make sure to subscribe to this channel and give a thumbs up. Now let's begin. The Andromeda Galaxy, catalogued as Messier 31 or M31 by astronomers, reigns as the largest galaxy in our local group, a cosmic neighborhood containing over 50 galaxies bound together by gravity. When we talk about Andromeda's size, we're actually discussing several different measurements, each revealing something profound about this galactic titan. There's its visible extent, its true physical diameter, including dark matter, its mass, and its stellar population. Each dimension tells a different story about this magnificent cosmic island. Let's start with what we can actually see. The visible disk of Andromeda stretches approximately 220,000 light-years across, making it roughly twice the diameter of our Milky Way's visible disk, which spans about 100,000 light-years. To put this in perspective, if you could somehow place these two galaxies side by side, Andromeda would dwarf our home galaxy. But even this comparison doesn't capture the full picture, because galaxies don't have sharp edges. They fade gradually into the darkness of intergalactic space. The Hubble Space Telescope, humanity's premier eye on the cosmos, has studied Andromeda in exquisite detail. Between 2010 and 2013, Hubble conducted an ambitious survey called the Panchromatic Hubble Andromeda Treasury, or PHAT. This groundbreaking project captured the largest and sharpest image ever taken of our galactic neighbor, resolving over 100 million individual stars within a region spanning approximately 61,000 light-years. This mosaic required over 7,000 individual exposures and represents one of the most detailed studies of any galaxy beyond our own. What the PHAT survey revealed is breathtaking. Andromeda contains regions of vigorous star formation where massive blue stars illuminate vast clouds of gas and dust. It harbors ancient globular clusters, dense spheres of elderly stars that formed when the galaxy was young. The observations mapped the galaxy's spiral arms in unprecedented detail, revealing the complex structure created by billions of years of galactic evolution. Every pixel in those images contains countless stories: stars being born, planets potentially forming, stellar remnants from long-dead suns. But Andromeda's visible light represents only part of the story. The Spitzer Space Telescope, which observed the universe in infrared wavelengths before its retirement in 2020, penetrated the cosmic dust that obscures visible light. These infrared observations revealed Andromeda's total stellar mass, the combined weight of all its stars. Current estimates suggest Andromeda contains approximately 1 trillion stars, compared to our Milky Way's 2 to 400 billion. Think about that for a moment. 1 trillion individual suns, each potentially hosting planets, each with its own life cycle, its own story written in fusion and gravity. The galaxy's spiral structure emerges from a delicate gravitational dance. Andromeda is classified as an SASB galaxy in the Hubble sequence, a spiral galaxy with tightly wound arms. These arms aren't solid structures but density waves, regions where stars and gas bunch up temporarily as they orbit the galactic center. It's like a cosmic traffic jam where cars, stars, slow down, creating a denser region that appears as a spiral arm, then speed up and exit on the other side. The arms themselves rotate around the galaxy at a different rate than the stars, creating this beautiful, enduring pattern. At Andromeda's heart lurks something extraordinary, not one, but two supermassive black holes orbiting each other. The primary black hole contains approximately 140 million times the mass of our Sun, while its companion weighs in at several tens of millions of solar masses. This discovery, made through careful analysis of stellar orbits near the galactic center, suggests that Andromeda experienced a major merger with another large galaxy in its past. When galaxies collide, their central black holes eventually spiral together, and Andromeda's dual black holes are likely remnants of such a cosmic collision. The European Space Agency's Gaia mission, launched in 2013, has revolutionized our understanding of stellar positions and motions. While Gaia primarily maps stars in our own Milky Way, it has also measured the precise motions of stars in Andromeda's outer regions. These observations have revealed something remarkable. Andromeda rotates in a way that suggests it's embedded within an enormous halo of dark matter. This invisible matter, which we can only detect through its gravitational effects, extends far beyond the visible galaxy. Dark matter halos are one of cosmology's most profound mysteries. We know they exist because galaxies rotate too fast. The visible matter alone doesn't provide enough gravity to hold them together at their observed rotation speeds. Stars in Andromeda's outer reaches orbit at hundreds of kilometers per second. Without dark matter's gravitational grip, these stars would fly off into intergalactic space. Current models suggest that Andromeda's dark matter halo might extend over 1 million light-years from the galaxy's center, though the halo's density decreases dramatically with distance. When we include this dark matter halo in our measurements, Andromeda becomes even more massive. The total mass of the galaxy, including all its stars, gas, dust, and dark matter, amounts to approximately 1.5 trillion times the mass of our Sun. For comparison, the Milky Way's total mass is estimated at roughly 800 billion to 1.5 trillion solar masses. Recent observations suggest these two galaxies might actually be quite similar in total mass, though Andromeda clearly has more stars and a larger visible extent. The spatial relationship between Andromeda and the Milky Way tells a cosmic story of connection and inevitable collision. These two galaxies orbit a common center of mass, slowly spiraling toward each other through the darkness of intergalactic space. Andromeda currently sits approximately 2.5 million light-years away from us, close enough that on the cosmic scale we're practically neighbors. The light you see when you observe Andromeda left that galaxy during the Pliocene epoch on Earth, when early hominids were just beginning to diverge from other primates. Speaking of cosmic distances and the challenges of traversing them, if you're curious about the incredible scale of even our local cosmic neighborhood, check out my video called "How Big is the Universe Compared to the Milky Way?" Discover how the Milky Way, as vast as it is just one of at least 2 trillion galaxies, and why even counting every grain of sand on Earth wouldn't match the number of stars in the cosmos. The link is in the description below and pinned on the comments. Now let's continue exploring the magnificent scale of Andromeda. Measuring Andromeda's approach velocity required decades of patient observation. Astronomers use the Doppler effect, the same phenomenon that makes an ambulance siren change pitch as it passes you. When objects move toward us, their light shifts toward bluer wavelengths. When they recede, the light shifts toward red. Andromeda's light shows a distinct blue shift, revealing its approach at approximately 110 kilometers per second relative to our Sun. This might sound fast, but at cosmic distances, it means Andromeda closes the gap by about 1 light-year every 9,000 years. The inevitable collision between Andromeda and the Milky Way will unfold over an immense time scale. Current simulations run on powerful supercomputers that model the gravitational interactions of billions of particles predict the first close passage will occur in approximately 3.8 to 4.5 billion years. But collision is a misleading term. The spaces between stars are so vast that almost no stars will actually collide. Instead, the two galaxies will pass through each other like ghosts, their gravity reshaping both structures dramatically. During the first passage, gravitational tides will fling stars outward, creating long streamers of stellar material. The galaxies will swing past each other, then fall back for a second encounter. Over billions of years, they'll merge and settle into a single, giant elliptical galaxy. Some astronomers have nicknamed this future merged galaxy Milky or Milkdromeda. By the time this merger completes, our Sun will have swollen into a red giant and consumed Earth, so humanity, if we still exist, will face far more immediate concerns than galactic collision. Computer models of this merger create stunning visualizations that you can find online. These simulations show the spiral arms being torn apart and reformed, stars being scattered into eccentric orbits, and eventually both galaxies losing their beautiful spiral structure to become a more uniform elliptical galaxy. The dual, supermassive black holes at the centers will spiral together over millions of years after the merger, eventually combining in a cataclysmic event that will send gravitational waves rippling across the universe. Andromeda's size becomes even more impressive when we consider its satellite galaxies. Just as the Milky Way has smaller dwarf galaxies orbiting it, like the large and small Magellanic Clouds visible from the southern hemisphere, Andromeda commands its own family of satellite galaxies. At least 14 dwarf galaxies orbit Andromeda, gravitationally bound to the massive spiral. The two brightest satellites, M32 and M110, are visible through amateur telescopes and have been known since the 18th century. M32 is a compact elliptical galaxy that orbits close to Andromeda's disk. Recent observations suggest that M32's proximity has actually carved a gap in Andromeda's disk, creating a ring-like structure. The gravitational interaction between these two galaxies demonstrates how even smaller companions can influence their giant host. M110, on the other hand, is a larger dwarf elliptical galaxy that may have been a spiral before Andromeda's gravity stripped away its outer regions. The discovery of Andromeda's satellite galaxies has revealed an intriguing puzzle. These dwarf galaxies don't orbit randomly. Many lie in a thin, planar structure, almost like a disk of satellites. This plane of satellites challenges our understanding of how satellite galaxies should be distributed. Dark matter simulations predict satellites should orbit in all directions, creating a roughly spherical distribution. The observed planar arrangement suggests either our dark matter models need refinement or that these satellites formed through a special process we don't yet fully understand. The Pan-Andromeda Archaeological Survey, or PANDAS, conducted using the Canada-France-Hawaii telescope between 2008 and 2011, mapped the outer regions of Andromeda and its satellites in unprecedented detail. This survey discovered several new dwarf galaxies and revealed tidal streams, ghostly ribbons of stars torn from satellite galaxies by Andromeda's gravity. These stellar streams trace out the orbital paths of destroyed satellites, providing a fossil record of Andromeda's cannibalistic past. One particularly dramatic tidal stream extends over 100,000 light-years, wrapping partially around Andromeda like a cosmic scarf. This stream likely originated from a dwarf galaxy that ventured too close and was shredded by tidal forces. The stars in this stream follow roughly the same orbit their parent galaxy once traced, slowly dispersing over billions of years. Eventually, these stars will be fully incorporated into Andromeda's halo, erasing any evidence of the satellite galaxy that once existed. Andromeda's chemical composition tells us about its stellar populations and formation history. Astronomers measure metallicity, the abundance of elements heavier than hydrogen, and helium to determine stellar ages. The first stars in the universe contained only hydrogen and helium from the Big Bang. Each subsequent generation incorporated heavier elements created in previous stars' fusion cores and scattered by supernovae. By measuring metallicity in different regions of Andromeda, astronomers can map out the galaxy's growth over cosmic time. The PHAT survey revealed that Andromeda's disk contains regions of varying metallicity, suggesting complex formation history. Some areas show enrichment levels similar to our solar neighborhood, indicating stellar populations of similar age. Other regions appear more metal-poor, hosting ancient stars formed when the galaxy was young. This chemical mapping creates a kind of archaeological record, allowing astronomers to reconstruct Andromeda's biography across billions of years. Star formation in Andromeda follows patterns both similar to and different from our Milky Way. The galaxy forms approximately one new solar mass of stars per year, roughly comparable to our galaxy's star formation rate of about 2 to 3 solar masses annually. However, Andromeda's star formation isn't uniformly distributed. It concentrates in a peculiar ring-like structure at about 30,000 light-years from the galactic center, a feature that has puzzled astronomers since its discovery. This star-forming ring appears in ultraviolet observations from the Galaxy Evolution Explorer, or GALEX, spacecraft, which operated from 2003 to 2013. The ring glows brilliantly in ultraviolet light because young, massive stars emit most of their energy at these short wavelengths. These stellar nurseries contain vast molecular clouds where gravity compresses gas until it ignites nuclear fusion, birthing new stars. The ring's existence suggests some dynamic process, perhaps a past collision with another galaxy, organized Andromeda's gas into this distinctive pattern. The Spitzer Space Telescope's infrared observations revealed even more intricate structure within Andromeda's disk. Infrared light penetrates the cosmic dust that obscures visible wavelengths, exposing hidden star formation regions. Spitzer discovered that Andromeda's spiral arms contain massive complexes of young stars, some comparable in size to the largest star-forming regions in our own galaxy. These stellar nurseries birth stars in clusters, gravitationally bound groups that will eventually disperse as they orbit the galaxy. Globular clusters orbit Andromeda in abundance. Approximately 450 have been identified, compared to about 150 in the Milky Way. These ancient stellar cities contain hundreds of thousands to millions of stars packed into spherical regions only tens of light-years across. The stars in globular clusters formed together billions of years ago, making them among the oldest objects in the galaxy. By studying their ages and chemical compositions, astronomers can constrain when Andromeda itself formed. Some of Andromeda's globular clusters are genuinely bizarre. Astronomers have discovered clusters with multiple stellar populations, different generations of stars with distinct chemical compositions. This challenges the traditional view that globular clusters formed in a single burst. Perhaps these clusters experience secondary star formation, or maybe they're remnants of dwarf galaxies that merged with Andromeda, bringing their own stellar populations. Each globular cluster holds clues to the galaxy's complex evolutionary history. The Hubble Space Telescope has resolved individual stars in some of Andromeda's globular clusters, allowing precise age determinations. By examining the cluster's Hertzsprung-Russell diagram, a plot of stellar brightness versus temperature, astronomers can identify the main sequence turn-off point where stars begin evolving into red giants. This turn-off point depends on stellar age, providing a cosmic clock. The oldest globular clusters in Andromeda appear to be approximately 13 billion years old, nearly as ancient as the universe itself. Andromeda's disk exhibits warping. The outer regions don't lie in a single plane, but curve upward on one side and downward on the other, like a potato chip. This warping likely results from gravitational interactions with its satellite galaxies, particularly M32 and M110. As these companions orbit, their gravity tugs on Andromeda's disk, creating ripples and distortions that propagate outward. Similar warping affects our Milky Way, possibly caused by the gravitational influence of the Large Magellanic Cloud. Gas in Andromeda's disk follows intricate patterns revealed by radio telescope observations. The 21-centimeter emission line of neutral hydrogen allows astronomers to map cold gas throughout the galaxy. These observations show that Andromeda contains approximately 5 billion solar masses of hydrogen gas, fuel for future star formation. The gas doesn't distribute uniformly but concentrates in the spiral arms and the star-forming ring, where it will eventually collapse to birth new stars. The Very Large Array Radio Telescope in New Mexico and the Westerbork Synthesis Radio Telescope in the Netherlands have mapped Andromeda's hydrogen in detail, revealing velocities that allow three-dimensional reconstruction of the gas distribution. This reveals that the gas disk extends beyond the visible stellar disk, reaching out to approximately 150,000 light-years from the galactic center. This extended gas disk represents Andromeda's fuel reserves, material that will support star formation for billions of years to come. Molecular clouds, dense concentrations of molecular hydrogen where stars form, pepper Andromeda's disk. These clouds appear dark in visible light because dust within them absorbs starlight, but they glow in specific molecular emission lines detectable by radio telescopes. Carbon monoxide, or CO, serves as a tracer for molecular hydrogen because it emits radio waves more readily. By mapping CO emission, astronomers locate the densest concentrations of star-forming material. The Institut de Radioastronomie Millimétrique 30-meter telescope and other facilities have identified hundreds of giant molecular clouds in Andromeda, some containing millions of solar masses of gas. The largest molecular cloud complexes rival anything found in the Milky Way. Within these clouds, turbulence, magnetic fields, and gravity battle for dominance. Where gravity wins, the cloud fragments and collapses, forming new stars. Understanding this process in Andromeda helps astronomers develop universal models of star formation applicable across different galactic environments. Dust lanes trace Andromeda's spiral arms, appearing as dark ribbons silhouetted against the galaxy's bright starlight. This cosmic dust consists of tiny particles, silicates, carbon grains, and ice-coated specks smaller than smoke particles. Despite being incredibly sparse by terrestrial standards, the dust concentration wouldn't qualify as a vacuum by laboratory standards. Accumulated across thousands of light-years, dust significantly affects our view of the galaxy. It absorbs and scatters blue light more effectively than red light, making dust-obscured regions appear redder. The Herschel Space Observatory, which operated from 2009 to 2013, observed Andromeda in far infrared and submillimeter wavelengths where dust radiates most strongly. These observations revealed the temperature and distribution of dust throughout the galaxy. Cooler dust concentrates in the spiral arms and molecular clouds, while warmer dust surrounds star-forming regions heated by young, luminous stars. The total dust mass in Andromeda amounts to approximately 30 million times the Sun's mass, a tiny fraction of the galaxy's total mass, but crucial for star and planet formation. X-ray observations of Andromeda reveal a completely different aspect of the galaxy, its population of compact objects and hot gas. The Chandra X-ray Observatory and XMM Newton have catalogued over 900 X-ray sources within Andromeda. Many of these are X-ray binaries, systems where a normal star orbits a neutron star or black hole. As material from the companion star spirals onto the compact object, it heats to millions of degrees, emitting copious X-rays. These systems represent stellar evolution's end stages, showcasing the exotic remnants of massive stars. Some X-ray sources in Andromeda shine with incredible luminosity, exceeding 100,000 times the Sun's total energy output. These ultraluminous X-ray sources, or ULXs, have challenged our understanding of stellar mass black holes. Traditional theory suggests black holes formed from single stars shouldn't exceed about 20 to 30 solar masses, yet some ULXs seem to require more massive black holes or alternative explanations involving extreme accretion physics. Studying Andromeda's ULX helps astronomers understand these mysterious objects. Supernovae in Andromeda provide cosmic laboratories for studying stellar death. Because we know Andromeda's distance quite precisely, approximately 2.54 million light-years based on observations of Cepheid variable stars and other distance indicators, supernovae discovered there serve as calibration points for cosmological distance measurements. Amateur astronomers, professional surveys, and automated telescope networks monitor Andromeda, hoping to catch the brilliant flash when a massive star explodes or a white dwarf detonates. The last supernova observed in Andromeda visible to the naked eye might have occurred in 1985, designated SN 1985P. However, this event's classification remains uncertain. It might have been a lesser outburst called a luminous red nova. Before that, astronomers documented a probable supernova in Andromeda in 1885, called S Andromedae. This event briefly rivaled Andromeda's nucleus in brightness, reaching 6th magnitude, just at the edge of naked eye visibility. For a few weeks, a single exploding star outshone hundreds of billions of ordinary stars. The rate of supernovae in a galaxy correlates with its star formation rate and stellar mass. Based on Andromeda's properties, astronomers estimate approximately 2 to 3 supernovae should occur per century. Many go undetected because they occur behind dust clouds or on the galaxy's far side where crowded star fields make detection difficult. Modern automated surveys like the Zwicky Transient Facility continuously monitor Andromeda and other nearby galaxies, catching more events than ever before. Nova eruptions, smaller stellar explosions involving white dwarfs in binary systems, occur more frequently in Andromeda, with about 30 detected per year. These events happen when hydrogen from a companion star accumulates on a white dwarf's surface until pressure and temperature trigger runaway fusion. The resulting thermonuclear explosion blows off the accumulated material, and the cycle can repeat every few decades or centuries. Andromeda's nova population provides a statistical sample for understanding these recurrent stellar fireworks. Planetary nebulae in Andromeda mark where Sun-like stars recently died. When stars similar to our Sun exhaust their nuclear fuel, they shed their outer layers, creating beautiful glowing shells of ionized gas. The Planetary Nebula Spectrograph Survey identified hundreds of planetary nebulae in Andromeda's halo and disk. Because planetary nebulae fade within tens of thousands of years, those we see today formed recently. Counting them provides an estimate of Andromeda's stellar death rate. Approximately 1 solar mass star dies every few decades. The kinematics of Andromeda's stellar populations reveal the galaxy's rotation and internal motions. Stars in the disk orbit the galactic center at hundreds of kilometers per second, with the rotation curve, a plot of orbital velocity versus distance from center, revealing the distribution of mass. Halo stars move on more eccentric orbits, plunging through the disk and swinging back out in elliptical trajectories. Globular clusters follow their own complex orbital patterns, many on highly elongated paths that carry them far from the galactic center. Andromeda's rotation curve extends far beyond the visible disk, remaining flat, meaning orbital velocities stay constant out to enormous distances. This flat rotation curve provides some of the most compelling evidence for dark matter. If only visible matter existed, orbital velocities should decline with distance, following Kepler's laws like planets orbiting the Sun. The constant velocities indicate that mass continues to increase with radius, even where we see no stars or gas. This invisible mass is dark matter. Multiple techniques have measured Andromeda's rotation. Optical spectroscopy measures Doppler shifts of stellar absorption lines, revealing stellar velocities along our line of sight. Radio observations of neutral hydrogen trace gas velocities throughout the disk. Each measurement method contributes to our understanding of how mass distributes throughout the galaxy. Combining these techniques creates a comprehensive picture of Andromeda's gravitational architecture. The Andromeda Milky Way system doesn't exist in isolation. It's part of the Local Group, a collection of over 50 galaxies occupying a volume approximately 10 million light-years across. The third major member of this group is the Triangulum Galaxy, or M33, a smaller spiral containing perhaps 40 to 60 billion stars. Triangulum orbits Andromeda at a distance of about 750,000 light-years, and some evidence suggests it might be gravitationally bound to the larger galaxy. The local group's dynamics reveal the interplay between cosmic expansion and gravity. While the universe expands on the largest scales, carrying distant galaxies away from each other, gravity binds the local group together. The galaxies within our group aren't participating in cosmic expansion. They're gravitationally bound, orbiting each other like a cosmic dance. Andromeda and the Milky Way dominate this system, their combined gravity shaping the motions of all the smaller members. Dark matter's role in Andromeda becomes even more apparent when we consider the galaxy's escape velocity, the speed needed to leave the galaxy permanently. At the Sun's distance from the Milky Way's center, escape velocity is approximately 550 kilometers per second. For Andromeda, with its greater mass, escape velocity at equivalent distances reaches similar or slightly higher values. These high escape velocities, far exceeding what visible matter alone could produce, demonstrate that dark matter's gravitational grip extends throughout the galaxy. Recent observations using the Hubble Space Telescope have measured Andromeda's proper motion, its sideways motion across the sky, with extraordinary precision. By comparing the positions of stars in Andromeda against distant background galaxies over several years, astronomers determined that Andromeda moves tangentially at approximately 60 kilometers per second. Combined with its radial velocity toward us, this allows calculation of Andromeda's three-dimensional motion through space. These measurements refine predictions of when and how the Milky Way-Andromeda collision will unfold. The halo of Andromeda extends far beyond the visible galaxy, filled with ancient stars and globular clusters. This stellar halo appears relatively smooth and featureless in shallow observations, but deep surveys reveal intricate substructure, streams, shells, and overdensities that mark where smaller galaxies merged with Andromeda in the past. Each merger leaves a gravitational scar, a temporary disturbance in the halo's stellar distribution that fades over hundreds of millions of years but remains detectable with sensitive observations. The giant stellar stream in Andromeda's halo represents one of the most prominent merger remnants. This structure, discovered in 2001 using data from the Isaac Newton telescope, arcs across the galaxy's outskirts, stretching over hundreds of thousands of light-years. Computer simulations suggest it originated from a dwarf galaxy that merged with Andromeda roughly 700 million years ago. The stream's stars follow similar orbits, marking the trajectory of their destroyed parent galaxy like breadcrumbs on a cosmic scale. Andromeda's stellar populations span a wide range of ages, from ancient stars nearly as old as the universe to bright young stars born within the last few million years. The galaxy's thick disk and halo contain primarily old stars with low metallicity. These stars formed early in the galaxy's history when the universe contained fewer heavy elements. The thin disk hosts younger stars with higher metallicity, born more recently from gas enriched by previous stellar generations. The youngest stars concentrate in spiral arms and star-forming regions, glowing blue and bright. Measuring stellar ages in distant galaxies presents significant challenges. Astronomers can't observe individual stars like our Sun at Andromeda's distance. They're simply too faint. Instead, they study stellar populations statistically, analyzing the combined light from millions of stars. By comparing observed colors and spectra against stellar evolution models, astronomers estimate the average age and metallicity of different regions. This technique, called population synthesis, reveals Andromeda's star formation history across cosmic time. The PHAT survey's unprecedented resolution allowed astronomers to construct color magnitude diagrams for different regions of Andromeda, plots showing individual stars' brightness versus color. These diagrams reveal the mixture of stellar types present: blue main sequence stars burning hydrogen, red giants nearing the end of their lives, asymptotic giant branch stars puffing off their outer layers, and white dwarfs cooling slowly over billions of years. Each stellar population tells part of Andromeda's story. Star clusters in Andromeda range from young open clusters containing dozens to thousands of stars loosely bound by gravity, to ancient globular clusters with hundreds of thousands of stars tightly packed. Open clusters form within molecular clouds and gradually disperse over hundreds of millions of years as stellar encounters and galactic tidal forces pull them apart. The youngest open clusters in Andromeda, found in active star-forming regions, contain massive blue stars that illuminate their surroundings with ultraviolet radiation. Intermediate-age star clusters, between 1 and 10 billion years old, bridge the gap between young open clusters and ancient globulars. These clusters, more common in Andromeda than in the Milky Way, might form during galactic mergers when compression waves trigger intense star formation. Andromeda's excess of intermediate-age clusters suggests the galaxy experienced significant merger activity in its past, possibly explaining features like the star-forming ring and some tidal streams in the halo. The nucleus of Andromeda presents a puzzle. High-resolution Hubble observations revealed that the galaxy's center contains not one, but two brightness peaks, a double nucleus structure separated by about 5 light-years. For years, astronomers debated whether this represented two distinct stellar concentrations or an optical illusion. Recent observations suggest the double structure arises from an eccentric disk of stars orbiting the central supermassive black hole. We're seeing two edges of this disk, one approaching us and brightened by Doppler boosting, one receding and slightly dimmed. This eccentric stellar disk likely formed from stars on elongated orbits around the black hole, possibly created during a past galactic merger. When two galaxies combine, their central black holes eventually merge, but before that happens, gravitational interactions can scatter stars onto unusual orbits. The eccentric disk in Andromeda might be a fossil record of such an event, preserving evidence of a merger that occurred hundreds of millions or billions of years ago. Andromeda's center also contains a concentration of old, metal-rich stars, the galaxy's oldest stellar population. These stars formed early in the galaxy's history, sinking to the center through dynamical friction over billions of years. Studying these ancient stars provides clues about conditions when Andromeda first assembled. Their high metallicity surprises some astronomers because the earliest stars should be metal-poor. This suggests that Andromeda's central region experienced intense early star formation, rapidly enriching its gas with heavy elements. The bulge of Andromeda, the central spherical concentration of stars, extends approximately 12,000 light-years from the galactic center. This classical bulge differs from the pseudo-bulges found in some spiral galaxies, which form from disk material funneled inward. Andromeda's bulge likely formed early in the galaxy's history through violent processes, either the rapid collapse of primordial gas or the merger of smaller proto-galactic fragments. Its stellar populations resemble those in elliptical galaxies, dominated by old, red stars on randomly oriented orbits. Observations across the electromagnetic spectrum reveal different aspects of Andromeda's bulge. Infrared observations penetrate dust to see the underlying stellar distribution, showing that the bulge is somewhat boxy rather than perfectly spherical, a sign of complex dynamics. X-ray observations reveal hot gas at millions of degrees, heated by stellar winds from evolved stars and supernova remnants. Radio observations detect synchrotron emission from relativistic electrons spiraling in magnetic fields, tracing energetic processes occurring near the galactic center. The magnetic field threading Andromeda's disk plays crucial but often overlooked roles in galactic dynamics. Magnetic fields affect star formation by providing pressure support against gravitational collapse in molecular clouds. They channel charged particles, creating cosmic rays that permeate the galaxy. Radio polarization observations allow astronomers to map magnetic field structure, revealing large-scale spiral patterns that loosely follow the stellar spiral arms but show their own distinct topology. Andromeda's magnetic field strength reaches several microgauss in the disk, roughly 1,000,000 times weaker than Earth's magnetic field, but still dynamically significant on galactic scales. The field's spiral structure suggests it's amplified and organized by the galaxy's rotation through a process called the dynamo effect. As the galaxy rotates differentially, inner regions rotating faster than outer ones, it winds up and amplifies weak seed magnetic fields, creating the large-scale structure observed today. Cosmic rays in Andromeda, high-energy particles accelerated to near light speed, interact with the galactic magnetic field, creating synchrotron radiation detectable at radio wavelengths. The most powerful cosmic ray accelerators in the galaxy are supernova remnants, where shock waves from stellar explosions energize particles. As these relativistic particles spiral along magnetic field lines, they emit radio waves. Mapping this emission reveals both the magnetic field structure and the distribution of cosmic ray sources. The Fermi Gamma Ray Space Telescope has detected high-energy gamma rays from Andromeda, though much fainter than emissions from our own galaxy's center. These gamma rays likely originate from cosmic rays colliding with interstellar gas, producing pions that decay into gamma rays. The detection confirms that Andromeda, like the Milky Way, maintains a population of cosmic rays throughout its volume. Studying gamma ray emission from external galaxies helps astronomers understand whether our galaxy's cosmic ray properties are typical or unusual. Environmental factors influence Andromeda's evolution. The galaxy doesn't exist in perfect isolation but interacts with its surroundings, the hot, tenuous gas filling intergalactic space, the gravitational influence of nearby galaxies, and the cosmic web's large-scale structure. These environmental effects, though subtle, shape the galaxy over billions of years. Gas accretion from the intergalactic medium might fuel ongoing star formation, while gravitational interactions with satellites trigger disturbances that propagate through the disk. The circumgalactic medium surrounding Andromeda, hot gas, extending hundreds of thousands of light-years beyond the visible galaxy, has been mapped using ultraviolet observations of background quasars. When light from a distant quasar passes through Andromeda's halo, gas clouds absorb specific wavelengths, creating absorption lines in the quasar's spectrum. By studying many sight lines through the halo, astronomers map the gas distribution, revealing how Andromeda interacts with its environment. This hot halo gas heated to hundreds of thousands of degrees, might contain as much mass as all the stars in the galaxy combined. It represents Andromeda's reservoir, gas that has fallen partway toward the galaxy but hasn't yet cooled enough to join the disk and form stars. Understanding this circumgalactic medium helps explain how galaxies acquire the gas they need for star formation and how feedback from the galaxy, stellar winds, supernova explosions, black hole jets, affects the surrounding environment. The cosmic web positions Andromeda within a filament of the universe's large-scale structure. Galaxies aren't distributed randomly but concentrate along filaments connecting massive galaxy clusters. The local group containing Andromeda and the Milky Way sits within one such filament, being pulled toward the Virgo cluster approximately 54 million light-years away. This cosmic flow affects the entire local group's motion through space, demonstrating how structure on 100 million light-year scales influences our local galactic neighborhood. Simulations of cosmic structure formation successfully reproduce galaxies like Andromeda. Cosmologists use supercomputers to model dark matter's gravitational collapse from the early universe's tiny density fluctuations. These simulations show dark matter clumping into halos with masses and structures similar to observations. When astronomers add gas physics, cooling, star formation, feedback, the simulations produce realistic spiral galaxies resembling Andromeda in many properties. However, some discrepancies remain between simulations and observations. The satellite plane problem, Andromeda's satellites concentrating in a thin disk, contradicts simulation predictions. Similarly, simulations tend to produce denser galaxy centers than observations show, the so-called core cusp problem. These tensions might indicate missing physics in simulations, or they might suggest our dark matter model needs refinement. Andromeda serves as a crucial test case for cosmological theories because its proximity allows detailed observations unavailable for more distant galaxies. The assembly history of Andromeda, how it grew from small proto-galactic fragments into today's magnificent spiral, can be partially reconstructed from observations of its stellar populations and structure. Chemical abundance patterns in different regions reveal the pace of star formation over cosmic time. Tidal streams mark past merger events. The mix of stellar ages constrains when major growth episodes occurred. Together, these clues sketch a biography of a galaxy that has evolved for over 13 billion years. Current evidence suggests Andromeda experienced a major merger approximately 2 to 3 billion years ago, quite recent on cosmic timescales. This merger likely involved a galaxy with perhaps 1/5 of Andromeda's mass. The collision would have disrupted both galaxies' structures, triggering intense star formation as gas clouds compressed and collided. Many of the tidal streams now visible in Andromeda's halo might originate from this event, along with the peculiar star-forming ring and possibly the dual supermassive black holes. Before this recent major merger, Andromeda assembled more gradually through accretion of smaller satellites, the hierarchical assembly predicted by cosmological simulations. Small dark matter halos merged to form larger ones, with gas cooling and forming stars within these gravitational wells. Each merger added stars, gas, and dark matter, slowly building the massive galaxy we see today. The globular clusters orbiting Andromeda might be remnants of these early building blocks, survivors that avoided destruction during mergers. Star formation history reconstruction suggests Andromeda formed stars vigorously early in cosmic history, with a peak around 8 to 10 billion years ago during the epoch astronomers call cosmic noon, when star formation rates peaked across the universe. Since then, star formation has gradually declined, though it continues today in molecular clouds scattered throughout the disk. This life cycle, vigorous youth followed by gradual decline, appears common among massive galaxies. The similarity between Andromeda and the Milky Way extends beyond their physical properties. Both are large spiral galaxies, both host supermassive black holes, both have similar masses when dark matter is included, and both dominate their local environments with families of satellite galaxies. Yet, subtle differences exist. Andromeda has more stars, a larger disk, and possibly a more active merger history. Comparing these cosmic twins helps astronomers understand which galactic properties are universal and which depend on specific evolutionary histories. Observing Andromeda from Earth provides perspectives impossible from within our own galaxy. We see Andromeda at a slight tilt, its disk inclined about 77 degrees to our line of sight. This orientation allows us to study its spiral structure, disk dynamics, and stellar populations with a global view unavailable for the Milky Way. Our position inside the Milky Way makes mapping our own galaxy's structure difficult, like trying to map a forest while standing among the trees. Andromeda offers an external view of a similar galaxy, illuminating what our galaxy might look like from afar. Amateur astronomers have long treasured Andromeda as a showpiece object. Visible to the naked eye from dark sites, it appears as a fuzzy oval patch in the constellation Andromeda. Through binoculars, its elongated shape becomes apparent, with the bright nucleus standing out. Small telescopes reveal its two bright satellite galaxies, M32 and M110, appearing as small, fuzzy patches near the larger galaxy. Larger amateur telescopes under dark skies can detect dust lanes and hints of spiral structure in Andromeda's disk. Photography revolutionizes Andromeda viewing for amateurs. Long exposure images captured even with basic camera equipment reveal details invisible to the eye: spiral arms traced by blue star-forming regions and reddish nebulae, dust lanes silhouetted against background starlight, the extensive halo surrounding the bright disk. Modern digital cameras, cooled CCD sensors, and image processing software allow dedicated amateur astronomers to produce images rivaling professional observations from decades past. The historical study of Andromeda traces back over 1,000 years. Persian astronomer Abd al-Rahman al-Sufi described it in 964 as a small cloud. In his Book of Fixed Stars, the first known reference to the object, European astronomers catalogued it in the 17th and 18th centuries, including Charles Messier, who listed it as M31 in his famous catalogue of nebulous objects. But its true nature remained mysterious until the 20th century. The Great Debate of 1920 epitomized the controversy over Andromeda's nature. Astronomers Harlow Shapley and Heber Curtis argued about whether spiral nebulae like Andromeda were relatively small objects within our Milky Way or separate island universes comparable to our galaxy. Shapley argued for a large Milky Way containing all nebulae. Curtis proposed that spiral nebulae were distant galaxies. The debate remained unresolved until 1923. Edwin Hubble's observations with the Mount Wilson Observatory's 100-inch Hooker telescope, then the world's largest, settled the question. Hubble identified Cephid variable stars in Andromeda's outskirts. Cephids pulsate with periods related to their intrinsic brightness, a property discovered by Henrietta Swan Leavitt. By measuring a Cephid's period and apparent brightness, astronomers can calculate its distance. Hubble's Cephids revealed Andromeda lay approximately 900,000 light-years away, vastly farther than the Milky Way's extent. Andromeda was indeed a separate galaxy. Hubble's discovery revolutionized astronomy, expanding the known universe tremendously. The Milky Way was no longer the entire cosmos, but one galaxy among countless others. This paradigm shift ranks among the most profound in scientific history, comparable to Copernicus removing Earth from the universe's center, or Darwin revealing life's evolutionary connections. Suddenly the universe became vastly larger, filled with galaxies beyond number, each potentially containing billions of stars and untold worlds. Modern distance measurements to Andromeda use multiple techniques, cross-checked for consistency. Cepheid variables remain important, but astronomers also employ other standard candles like RR Lyrae variables, red giant branch stars, and planetary nebulae. The Hubble Space Telescope's observations of Cepheids in Andromeda, combined with improved calibrations, place the galaxy at approximately 2.54 million light-years, nearly 3 times more distant than Hubble's original estimate. Early measurements suffered from calibration errors and confusion between different types of variable stars. This accurate distance measurement matters because Andromeda serves as a stepping stone for measuring distances to more remote galaxies. The cosmic distance ladder builds from nearby measurements using parallax, the apparent shift of nearby stars as Earth orbits the Sun, through Cepheids and other standard candles in nearby galaxies, ultimately reaching cosmological distances where galaxy redshifts measure expansion. Each rung depends on the previous one, so errors propagate and compound. Precisely measuring Andromeda's distance anchors this crucial chain. The tip of the red giant branch method provides an independent distance estimate to Andromeda. Red giant branch stars reach a maximum luminosity, a brightness limit set by helium flash physics, creating a sharp cutoff in the galaxy's stellar luminosity function. By identifying this tip in Andromeda's stellar population and comparing its apparent brightness to the known absolute brightness, astronomers calculate distance. This method's distance agrees with Cepheid measurements within uncertainties, boosting confidence in both techniques. Surface brightness fluctuations offer yet another approach. Distant galaxies appear smooth because individual stars blur together, but statistical fluctuations in how stars distribute create subtle graininess. The amplitude of these fluctuations depends on distance. More distant galaxies appear smoother. By carefully measuring this graininess in Andromeda's stellar populations, astronomers derive distance estimates independent of other methods. Again, the results agree remarkably well, confirming Andromeda's distance with high confidence. Why does Andromeda's precise distance matter? Beyond calibrating the cosmic distance ladder, it allows accurate determination of the galaxy's physical properties. Knowing distance converts angular measurements into physical sizes and apparent brightnesses into absolute luminosities. Without accurate distance, we couldn't confidently state Andromeda's diameter, mass, or star formation rate. Every physical quantity depends on distance. It's the fundamental parameter from which all else follows. Andromeda also serves as a laboratory for testing stellar evolution models. Because all stars in the galaxy lie at essentially the same distance, differences in apparent brightness directly reflect differences in intrinsic luminosity. This allows construction of pristine color magnitude diagrams uncontaminated by distance uncertainties. Astronomers compare these diagrams against theoretical stellar evolution tracks, testing whether models correctly predict how stars of different masses evolve over time. The chemical evolution of galaxies, how heavy element abundances change over cosmic time, finds important tests in Andromeda. Observations reveal abundance gradients. The inner galaxy shows higher metallicity than outer regions. This gradient reflects inside-out galaxy formation, where the center forms stars earliest and most vigorously, quickly enriching its gas, while the outskirts form stars more slowly over longer periods. The gradient's steepness and shape constrain models of gas flow, star formation efficiency, and supernova feedback. Specific elements trace different stellar processes. Alpha elements like oxygen, magnesium, and silicon form in massive stars and scatter quickly via core collapse supernovae. Iron forms primarily in type Ia supernovae, white dwarf explosions that occur hundreds of millions of years after star formation. The ratio of alpha elements to iron thus indicates star formation timescales. Andromeda's stellar populations show varying alpha to iron ratios, revealing different star formation histories in the bulge, disk, and halo. Nitrogen enrichment tells another story. Nitrogen forms partly in massive stars, but primarily in intermediate mass stars during their asymptotic giant branch phase. These stars evolve more slowly than massive stars, creating a time delay between carbon and nitrogen enrichment. By measuring nitrogen abundances alongside carbon and oxygen, astronomers reconstruct the sequence of stellar generations that enriched Andromeda's gas over billions of years. The neutron capture elements like europium and barium form through neutron-rich nuclear processes in evolved stars and supernovae. These elements' abundances provide clues about the earliest stellar generations and the proportion of different supernovae types. Some globular clusters in Andromeda show unusual neutron capture element patterns, suggesting they formed in unique environments, perhaps in dwarf galaxies with different chemical evolution before merging into Andromeda. Lithium abundances present a cosmic puzzle. Big Bang nucleosynthesis created lithium in the universe's first minutes, and low-mass stars preserve primordial lithium in their atmospheres. However, observed lithium abundances fall below theoretical predictions, the cosmological lithium problem. Studying lithium in Andromeda's stars helps determine whether this discrepancy indicates new physics in the early universe or astrophysical processes we don't fully understand. Andromeda's role in our cosmic future extends beyond the eventual merger. As dark energy drives cosmic expansion to accelerate, the universe's large-scale structure evolves in profound ways. Galaxy clusters drift apart, isolated by ever-increasing distances. The local group, gravitationally bound, resists this expansion, remaining a coherent structure even as the wider universe empties around it. Eventually, in tens or hundreds of billions of years, the merged Andromeda Milky Way system will find itself increasingly isolated in an expanding void. Future astronomers in this merged galaxy will face a universe transformed beyond recognition. Nearly all galaxies outside the local group will have receded beyond the cosmic horizon, their light redshifted to undetectability. The cosmic microwave background will have cooled and stretched to wavelengths spanning meters or kilometers, becoming effectively unobservable. Evidence for the Big Bang, cosmic expansion, and the universe's true scale will vanish. Without access to preserved knowledge from our era, these distant descendants might conclude their galaxy is the entire universe, ironically returning to the pre-Hubble view. This scenario emphasizes how privileged our cosmic epoch is for astronomy. We live when the universe has matured enough to form complex structures and observers, but hasn't yet expanded so much that cosmic history becomes invisible. The observable universe currently reveals its past with remarkable clarity. The cosmic microwave background shows us the infant universe, distant galaxies reveal cosmic evolution, and nearby objects like Andromeda provide detailed views of galactic structure. Future civilizations won't have this wealth of evidence. The philosophical implications run deep. Our understanding of the cosmos depends not just on our intelligence and technology, but on when we exist in cosmic history. Observers at different epochs face different evidential landscapes. What seems fundamental and obvious to us, cosmic expansion, the Big Bang, dark energy, might be inaccessible to future astronomers. Conversely, we might be blind to aspects of reality that other epochs would find obvious. This contingency of knowledge humbles our certainty and suggests we should remain open to possibilities beyond our current observational reach. Andromeda also figures in humanity's long-term survival prospects. If our descendants survive the Sun's eventual red giant phase, when it swells to consume the inner planets including Earth, they'll need to find new homes. The Andromeda-Milky Way merger will create billions of new habitable zones as stars are scattered onto new orbits. Planets will find themselves in different regions of the merged galaxy, experiencing different radiation environments, stellar densities, and cosmic ray fluxes. However, the merger poses challenges. Close stellar encounters, while rare, will become more frequent. Planetary systems might be disrupted, with planets ejected into interstellar space or plunging into their stars. The intense star formation triggered by colliding gas clouds will produce numerous supernovae bathing portions of the galaxy in deadly radiation. Navigating these dangers will require technology and foresight far beyond our current capabilities, assuming humanity or its descendants still exist billions of years hence. Some science fiction has imagined civilizations deliberately manipulating the Andromeda-Milky Way collision, using advanced technology to steer galaxies, harvest energy from tidal interactions, or engineer favorable outcomes. While this remains firmly in the realm of speculation, it illustrates how cosmic events we consider inevitable might be controllable by sufficiently advanced civilizations. Perhaps distant descendants will view the merger not as an uncontrollable natural disaster, but as an engineering project. Andromeda's size also contextualizes our search for extraterrestrial intelligence. The galaxy contains approximately 1 trillion stars. If even a tiny fraction host technological civilizations, Andromeda might contain millions or billions of advanced societies. Yet we see no evidence of galaxy-wide engineering, no signatures of cosmic-scale technology. This silence, the Fermi paradox applied to Andromeda, suggests either technological civilizations are extraordinarily rare, they don't engage in galaxy-spanning expansion, or they exist in forms we don't recognize. The light travel time across Andromeda, approximately 220,000 years, poses fundamental limits on any civilization attempting galactic coordination. A message from one side to the other takes over 200 millennia. Building an empire or network spanning the galaxy would require patience over timescales exceeding human civilization's entire history. Perhaps this explains the Great Silence. Galactic communities might exist but operate on timescales so slow we wouldn't recognize their activities as organized intelligence. Andromeda's stellar density varies by location, affecting hypothetical civilizations' opportunities and challenges. Near the galactic center, stars pack closer together, making interstellar travel easier, but also increasing hazards from supernovae, gamma-ray bursts, and close stellar encounters. In the sparse outer disk, stars are safer from cosmic catastrophes, but separated by vast gulfs of interstellar space. The Goldilocks zone for galactic habitability might lie where we find ourselves, mid-disk with moderate stellar density balancing opportunity and danger. Contemplating Andromeda's scale, 220,000 light-years across, 1 trillion stars, 13 billion years of history, we confront the cosmos's staggering scope. Each star potentially hosts planets. Each planet potentially harbors environments where chemistry becomes biology. Each world might develop unique ecosystems, possibly including intelligence and technology. The possible diversity of conditions, outcomes, and stories within Andromeda alone exceeds human imagination. Yet we've mapped this galaxy's structure, measured its motion, reconstructed its history, and predicted its future. Humans, ephemeral beings on a small planet orbiting an ordinary star, have comprehended a structure containing 1 trillion suns. This achievement ranks among consciousness's greatest triumphs, matter organized as human brains, understanding matter organized as galaxies. We are, in physicist Carl Sagan's words, a way for the cosmos to know itself. The pursuit of understanding Andromeda continues with ever more sophisticated tools. The James Webb Space Telescope, with its unprecedented infrared sensitivity, can resolve individual stars in Andromeda's outskirts and peer through dust to see hidden star formation. The upcoming extremely large telescope, with its 39-meter mirror, will resolve features just light days across at Andromeda's distance, allowing detailed study of individual stellar systems. The Nancy Grace Roman Space Telescope will survey vast regions of Andromeda, cataloguing hundreds of millions of stars and mapping the galaxy's structure in exquisite detail. Future gravitational wave observatories might detect signals from stellar mass black hole mergers within Andromeda. The Laser Interferometer Space Antenna, or LISA, planned for the 2030s, could potentially detect supermassive black hole mergers if Andromeda's dual black holes eventually spiral together. Each new observatory opens fresh windows on the galaxy, revealing phenomena invisible to previous instruments and answering questions while raising new mysteries. Andromeda's size places it among the universe's larger spiral galaxies, but not the largest. Some spirals span over 500,000 light-years, dwarfing even Andromeda. Giant elliptical galaxies in rich clusters can reach several million light-years across, containing tens of trillions of stars. Yet Andromeda represents the local benchmark, the magnificent nearby galaxy against which we compare all others. Its proximity makes it the most studied external galaxy, our primary laboratory for understanding galactic physics. The question, how big is Andromeda, admits multiple answers depending on what we measure. The visible stellar disk extends approximately 220,000 light-years. The neutral hydrogen disk reaches about 150,000 light-years. The dark matter halo might extend over 1 million light-years. The circumgalactic medium of hot gas stretches hundreds of thousands of light-years. Each definition captures a different aspect of this complex structure. Mass provides another size metric. Andromeda contains approximately 1 trillion stars, with combined mass around 1.5 trillion times our Sun. The total mass, including dark matter, reaches perhaps 1.8 trillion solar masses. By this measure, Andromeda roughly equals or slightly exceeds the Milky Way's mass, though uncertainties remain. The two galaxies are genuine peers, cosmic twins, separated by 2.5 million light-years, destined eventually to merge. Andromeda's gravitational influence extends even beyond its dark matter halo. The galaxy affects the motions of objects millions of light-years away through its gravitational pull. The entire local group orbits the combined center of mass of Andromeda and the Milky Way. Even distant dwarf galaxies feel these giants' gravity, their orbits shaped by forces originating in galaxies they'll never approach closely. Gravity's infinite reach means every massive object influences the entire universe, however slightly. The photons reaching our telescopes from Andromeda began their journey over 2 million years ago. They crossed the intergalactic void at light speed, traveling through expanding space, passing through sparse hydrogen clouds, penetrating Earth's atmosphere, and finally striking our detectors. Each photon carries information encoded in its wavelength, polarization, and arrival time, data we decode to reconstruct the distant galaxy's properties. Those ancient photons become knowledge, transforming from mere light into understanding. When you observe Andromeda, whether through a telescope, in a photograph, or even with naked eyes under dark skies, you're engaging in an act connecting you to the cosmos. The light entering your eye crossed 2.5 million light-years of space. It was emitted by stars, some now dead, whose nuclear fusion converted hydrogen to helium, releasing energy. That energy became photons that traveled across the universe to reach you. Your perception completes their journey, turning physics into consciousness, objective reality into subjective experience. This connection runs deeper than mere observation. The atoms composing your body were forged in stellar cores like those burning in Andromeda's stars. The calcium in your bones, the iron in your blood, the oxygen you breathe, all formed through nuclear fusion in stars that lived billions of years ago. Some of those stars might have been in galaxies that merged to build Andromeda or the Milky Way. You are literally made of stardust assembled from elements scattered by stellar explosions, gathered by gravity into new worlds, organized by evolution into conscious beings. Andromeda represents what we can achieve when we look up with curiosity rather than down with indifference. A century ago, we didn't know it was a galaxy. Today, we've mapped its structure, measured its distance, counted its stars, predicted its future, and pondered its meaning. This progression from ignorance to knowledge, from mystery to understanding, defines the scientific enterprise. Yet each answer spawns new questions about dark matter's nature, galaxy formation's details, cosmic evolution's trajectory. The vastness of Andromeda, 220,000 light-years, spanning billions of years of history, containing 1 trillion stars in a dance of gravity and light, inspires awe while teaching humility. We're tiny compared to such grandeur. Our lives briefly flickers against cosmic timescales. Yet we're also magnificent, able to comprehend what dwarfs us, to trace history across billions of years, to predict futures we'll never witness. This paradox, our simultaneous insignificance and significance, defines the human condition in a cosmic context. As we conclude this journey through Andromeda's dimensions, remember that numbers alone, 220,000 light-years, 1 trillion stars, 2.5 million light-years distant, can't capture the full reality. Behind those numbers lie countless individual stories, stars being born in molecular clouds, planets potentially forming in circumstellar disks, perhaps even civilizations asking their own questions about their place in the cosmos. Each star is a sun, each possible planet is a world, each world holds untold complexity. You now carry knowledge of Andromeda's scale, structure, and significance. When you next see that faint smudge in the night sky, you'll understand what you're seeing, not merely a fuzzy patch, but a galaxy of 1 trillion suns, spiraling through space, approaching our Milky Way in a cosmic dance that will culminate in a merger billions of years hence. You'll know that light striking your eye left that galaxy when our ancestors first walked upright, that the galaxy spans over 200,000 light-years, that it contains more stars than we can comprehend. This knowledge transforms observation into communion with the cosmos. You're not just seeing light, but perceiving a vast cosmic structure across 2.5 million light-years of space and 2.5 million years of time. You're connecting with the universe's grand story, from the Big Bang through cosmic evolution to the present moment. You're participating in humanity's ancient quest to understand our cosmic home, adding your awareness to the collective understanding built over generations. If you are still watching, make sure to give a thumbs up and subscribe to the channel. And if you enjoyed this video, this other one at the left side of the screen is a must-watch. How big is the solar system, and why we will never leave it? In this video, we explore the mind-bending distances within our own stellar backyard and the fundamental barriers to interstellar travel. See you there.